So, hi, this is Tim Shu from San Jose State University talking one more time about the definition of the limit. And so we'll start with a review of that definition, the epsilon-delta definition of the limit. We'll talk about what is a proof. So since the point of the definition is to do proofs, we'll have to say what that means. It boils down to a game, so we'll also talk about the structure of the game, and we'll spend most of the time on that because that's sort of what you'll be doing, including the last key part. Working backwards from epsilon to delta, and then finally we'll finish with an example of an epsilon-delta proof. Okay, so just to review what the definition says, to say that the limit of f of x as x approaches a is equal to L means that for every epsilon greater than 0, there exists some delta greater than 0, depending on epsilon, such that if the distance between x and a is less than delta, remember the absolute value of x minus a really means the distance between x and a is less than delta, and x is not equal to a, then the distance between f of x and L is less than epsilon. So this video answers the question, what is the point of that? So the short answer is, the point of having a definition like this is that it is precise enough that we can use this definition to prove that the limit of f of x as x approaches a is equal to L. Of course, that begs the question, what do we mean by proof? So we'll have a little digression here, but it's really one that's necessary. So what is a proof? Well, actually, before we can answer that, we actually need to think about an even bigger question. What is math? That is, what is theoretical math? So the world of proof-based math, so here's a very short version, the world of proof-based math has two kinds of objects. Definitions, which are things that we make up, and in which we must mutually agree as a starting point, otherwise you can't do anything. And theorems, or mathematical facts, which we logically deduce from the definitions. That's sort of the closest thing we have in this world to a fact on which everyone agrees. So put in those terms, a proof is a logical explanation of how a theorem follows from previously established definitions and theorems. Okay, so in our case, that means returning to the epsilon-delta definition of the limit to prove that the limit of f of x as x approaches a is equal to L, we need to explain why it is that for every epsilon greater than 0, there exists some delta greater than 0 depending on epsilon, such that if the distance between x and a is less than delta, and x is not equal to a, then the distance between f of x and L is less than epsilon. So how exactly do we go about doing that? Well, what we'll do here is that we'll peel away this definition layer by layer until we get a recipe that works for almost any epsilon-delta proof. Well, okay, real talk, this is only sort of a recipe. We'll see later why I only say sort of. In the end, this is kind of an art, and you can't really recipe it completely away. Anyway, that's to start off. Let's look at it piece by piece, starting with for every epsilon greater than 0. So to prove that some statement, blah, 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 is true for every epsilon greater than 0, we need to consider a random, sort of unknown epsilon greater than 0, and eventually logically deduce that blah, blah, blah is true for that epsilon greater than 0. So returning to our case, to prove that the limit of f of x as x approaches a is equal to L, we start the proof with assume epsilon is greater than 0. Remember, so we're trying to prove that the rest of the junk is true for every epsilon greater than 0. So we start by assuming we have some random unknown epsilon greater than 0. And then we explain, and eventually we're going to get to, we hope, there exists some delta greater than 0 depending on epsilon, such that if the distance between x and a is less than delta, and x is not equal to a, then the distance between f of x and L is less than epsilon. All right, so now we come to the weird step. So the next step, the sort of blue statement that we have to try to establish, is that there exists some delta greater than 0. So this is going to be weird. Well, so to prove that there exists some delta greater than 0 such that blah, blah, blah is true, what we need to do is we need to carefully choose, or really, to be honest, guess, some number delta greater than 0. In this case, that number delta, or expression greater than 0, delta greater than 0 must depend on epsilon. And eventually, we're going to deduce that blah, blah, blah is true for that particular delta greater than 0. So returning to our particular case, having started the proof with assume epsilon is greater than 0, we'll leave a space where we'll later on choose what delta is, delta greater than 0 is. So here we're going to let delta equal something, which we're going to figure out later, don't worry, depending on epsilon. And then after that, so, we start off the proof, assume epsilon is greater than 0, let delta equals, who knows, depending on epsilon, and then hopefully we'll give some more explanation, and eventually we'll end up at the conclusion that if the distance between x and a is less than delta, and x is not equal to a, then the distance between f of x and L is less than epsilon. Okay. So finally, that's the last bit that we have to explain how to explain. So the last bit, the purple and blue line, blue and purple lines, here they are, say in the form of an if-then statement. So to prove that if foo then bar is true, the way you do that is that you assume that foo is true, and you go through some logical explanation, and hopefully then arrive at the conclusion that bar is true. So in our case, after the beginning that we've already sort of figured out, assume epsilon is greater than 0, and then we let delta equals something we still haven't said what we're going to do, but it'll depend on epsilon. We're going to add, suppose the distance between x and a is less than delta, and x is not equal to a. And then we explain, and we hope, after some more logical explanation, we reach, so, the distance between f of x and L must be less than epsilon. Okay, so putting that all together, the takeaway is that any proof of a statement like the limit of f of x as x approaches a is equal to L looks like, assume that epsilon is greater than 0, we let delta be whatever, depending on epsilon, and we suppose that the distance between x and a is less than delta, and x is not equal to a, blah, 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 something magic happens here, and then eventually we get to the conclusion that the distance between f of x and L is less than epsilon. And the beauty of this, and now you should like freeze frame the slide and copy it down, or GIF it. That would be good. The point is that any epsilon delta proof goes like that. So at least you now have no excuse that when I ask you on homework and exams or whatever, prove that the limit of something is equal to something else. You have no excuse for having a blank page. Your proof should at least sort of start with this at the beginning and finish like that. All right, so when you're asked to prove that the limit of f of x as x approaches a is equal to L, your basic task is to start with that outline that we just discussed, that we went through such trouble to establish. We start here, and then you fill in the middle. Oh, also the question marks. Well, but here's where, remember I said that this is only sort of a recipe for doing epsilon delta proofs? Well, filling the middle is difficult, and every problem is different. And so that's why this is only sort of a recipe. There's at the heart of it, there's an art to it, and I can't really sort of recipe away the art, but at least we can sort of recipe away the other junk. So the way you do this is different for every problem, but one basic idea that often helps is to work backwards from the end, which says that the distance between f of x and L is less than epsilon, and you fiddle around with some algebra until you get something that looks like the distance between x and a is less than delta, and x is not equal to a. Or even, actually, the way the logic works, even if you only get the distance between x minus the distance between x and a is less than delta, that's good enough, because you might not even need, when you reverse it, it'll work out, and you might not need the assumption that x is not equal to a. Anyway, so that, like I just said, you take that algebra and reverse it, and you sort of hope that the logic still works in the other direction. Okay, so I'm sure that made no sense, because you're just sort of absorbing that as an abstract description, and you're not going to get into it unless you see at least one example. So here's one example. This is actually an example that's intentionally chosen to be harder than probably what you'll see in the homework, because I think students often complain that that the teacher does one that's too easy. Well, at least you won't have that complaint. You'll have the opposite one. Anyway, so let f of x be equal to 3 times x times the sine of 1 over x. Prove that the limit as x approaches 0 of f of x is equal to 0. So as our first pass, or sort of our first attempt, we start with exactly that kind of outline that we mentioned, that we spent all that time establishing. So like I said, every epsilon delta proof looks like this. So you assume that epsilon is greater than 0. We let delta be something, which we just haven't figured out what it's going to be yet, and we suppose the distance between x and 0 is less than delta, and x is not equal to 0. Remember, and this used to say a, but here we replaced the a with a 0 because we're looking at the limit as x approaches 0. And then there's some logical explanation, which we'll figure out later. But we know that the end says, so the absolute value of 3x sine of 1 over x minus 0 is less than epsilon. And so, again, our specific problem, except for these 3 or 4 little details, 1, 2, 3, 4, this is really completely generic, except we substituted a equals 0 over here, and we substituted f of x equals 3x sine of 1 over x over here, and we substituted L equals 0 over here. But otherwise, every problem at least sort of starts out like this. Okay, so there's at least a starting point. And so now the core of what we're doing is working backwards from going from epsilon to delta. So the idea is that we want to fiddle with the expression 3x sine of 1 over x minus 0, quantity absolute value of all that stuff is less than epsilon, until we can see how it somehow is relates to or is derived from the absolute value of x minus 0 is less than delta for some delta that we're going to get to choose. So that's where we get the flexibility in all this, is that if we can, as long as we can wrestle this to looking like that with only some expression in epsilon on the right hand side, then we win. Okay, so here's one way to do that. It's super not obvious, but after long experience, I happen to know this is how to do it, or at least one way to do it. So our starting point, remember, was this 3x sine of 1 over x minus 0 is less than epsilon, or the absolute value of that. And so the 0 goes away, and we start off with the absolute value of 3x sine of 1 over x is less than epsilon. With a little bit of algebra, we can divide both sides by 3 and get to the absolute value of x times sine of 1 over x is less than epsilon over 3. Okay. And now here comes the part that you really only learn how to do by experience. So at this point, we use a technique learned through experience. We recognize that the absolute value of sine of 1 over x, well, whatever that junk is, this is really something you can't control, but the point is it doesn't get very big. It can, it's the sine of something, and so its absolute value can be its size at most 1. So the worst case scenario of the left-hand side, the biggest the left-hand side can become, is the absolute value of x. So basically, I mean, this is just sort of distracting nonsense from the fact that basically what you have on the left-hand side is the absolute value of x. So if we happen to have the situation where the absolute value of x is less than epsilon over 3, which we can do because by choosing epsilon over 3 to be delta, or that is, in other words, guessing delta to be equal to epsilon over 3, what we get is that the absolute value of x times sine of 1 over x will be at most, will be less than or equal to the absolute value of x, which will then be strictly less than epsilon over 3. That's what we want. So delta unlocked, baby. Woo, woo. Okay, because I'm 12 years old, I'm making this blink artificially with the keyboard. But okay, you get the idea. So we figured out what delta is. If we pick delta equals epsilon over 3, then we can win. At least we think so. But the test of this, of course, is always writing it down to see if it really works. Okay, so putting that all together. So here's how the proof goes. So assume that epsilon is greater than 0. And let delta equals epsilon over 3. Why? Because we're really clever and we knew that was the way. Okay, of course, we went backwards and figured it out. So, but logically speaking, all you have to do there is just to choose delta equals epsilon over 3. And the justification for that choice just comes from, finishing the rest of the proof. So after that, and the next thing in the existing outline is that we suppose that the absolute value of x minus 0 is less than delta, which we know chose to be epsilon over 3, and that x is not equal to 0. In that case, because the absolute value of the sine of 1 over x is less than or equal to 1, sort of multiplying both sides of this by the absolute value of x, then we get that the absolute value of x times the sine of 1 over x is less than or equal to the absolute value of x. That's just sort of what we said. The worst case scenario of this left-hand side is when the left-hand side is actually equal to the absolute value of x. And so, when we do that, we see that the absolute value of x times the sine of 1 over x is less than or equal to the absolute value of x is less than epsilon over 3, because it says so right there. The absolute value of x is less than epsilon over 3. Therefore, multiplying both sides by 3, 3x times the sine of 1 over x minus 0 is less than epsilon, and we win! Woo! Go team! Okay, so I'm 12 years old. I really can't get over just like making that thing blink by my keyboard. All right. But yeah, we won. That's it. So again, as I often like to say, what are you waiting for? What are you wasting time watching me for? Go try some problems. Or actually, in this one particular case, you might want to watch this video again and go backwards and sort of see, and go look at where the definition how that definition becomes an outline, which I think might make more sense now that you've seen an example. So reread the text to look for more examples, and then try some problems. Anyways, thank you for your attention, and bye!